Good day. In this lecture, we will continue our discussion on polymers, focusing on their advanced classifications and properties. By the end of this lecture, you should be able to classify polymers based on composition, structure, and properties. Let's start by classification by backbone. The first is organic polymers, and these polymers have chains primarily composed of carbon atoms. Most synthetic polymers fall under this category, such as polyamides, polyesters, and PTFE. The next type is inorganic polymers, and these do not have carbon as their main backbone. These include glass and silicone-based materials. These often have different thermal and chemical properties as compared to that of organic polymers. Next is classification by structure. The first one is linear polymers, and these polymers consist of straight chain of repeating units. These form the basis of many thermoplastics such as PVC and HDPE. The next type of classification by structure is branch polymers, and these polymers have side chains attached to the main chain. This reduces packing efficiency and results in materials like LDPE, which are more flexible. The next type is cross-linked polymers, and these polymers have chains connected by covalent bonds, forming a network. Examples include vulcanized rubber and phenol formaldehyde. These structures are rigid and resistant to deformation. For the structural complexity of cross-linked polymers, cross-linking creates complex three-dimensional structures, and this significantly affects mechanical strength and thermal stability. The next one is classification by composition. The first polymer that we have there are homopolymers. Homopolymers are made up of one type of monomer. Examples include polyethylene and Teflon. The next type under classification by composition is copolymers. Copolymers are formed from two or more different monomers. Their arrangement determines their properties. Under copolymers, we have black copolymers. And in black copolymers, there are long sequences of one monomer alternating with another monomer. This gives distinct domains within the polymer. An example of that is styrene butadiene rubber. Another form of black copolymers are alternating and random copolymers. Alternating copolymers have regular pattern of monomers, while random copolymers have no fixed order. The last type of black copolymer are graph copolymers. And in graph copolymers, one polymer chain is branched onto another of different type. And this creates hybrid properties. The next type is classification based on molecular force. And the first polymer that we have there is elastomers. Elastomers are polymers that can stretch and return to their original shape. They consist of loosely connected chains with weak intermolecular forces. Their structures are composed of random coils of chains held by very weak intermolecular forces of attraction and form amorphous structures. This property is what allows them to be stretched. An example of elastomers are butane, buna-N, buna-S, neoprene, rubber, and spandex. Without cross-linking, deformation would be permanent. Cross-links provide elasticity and resilience to the elastomer. Applying stress to the elastomer will reconfigure their coiled structures to essentially straighten them out. Cross-links between chains then allow elastomers to return to their shape. When stretched, their chains align, and when released, they return to their coiled structure. Crosslink helps restore the elastomer to its original shape. The next type of polymer under molecular force are fibers. Fibers are long, thread-like polymers with high tensile strength. And the strong intermolecular forces such as hydrogen bonding allow for tight packing and also allows for the close bundling of chains which form the close crystalline structure of fibers. Example of fibers are silk, nylon 66 terylene, polyester, and cotton. The next type of resin under molecular force are liquid resins. And these are viscous polymers that can harden permanently. They are normally used as adhesives and sealants. Example of liquid resins are epoxy and polysulfide. Next is plastics. Plastics are polymers that can be molded into shape when heated. They may be rigid or semi-flexible depending on structure. Plastics are also polymers that are malleable when heated and can be molded into shape and hardened into rigid or semi-elastic materials. The plastic intermolecular forces of attraction are transition of elastomers and fibers, forming partially crystalline structures. This is the reason why plastics may be rigid or semi-elastic. Under plastics, we have thermoplastics and thermosets. Thermoplastics can be melted and reshaped multiple times, and they have linear or lightly branched structure with weaker intermolecular forces. Also, for thermoplastic, the chain bonds are easily broken through heating and easily reformed through cooling. Examples of thermoplastics are plastic bags, food containers, and garden hoses. Thermoplastics also include HDPE or high density polyethylene, LDPE, low density polyethylene, polypropylene, the PVC or polyvinyl chloride, and your PET, which is polyethylene terephthalate. Another type of plastics are thermosets. And when heated again, thermosets do not melt but instead decompose. This makes recycling difficult for thermosets. Thermosets possesses cross-link structure whose intermolecular forces of attraction are strong enough to prevent heat from easily breaking apart the chain bonds. Examples of thermosets include plastic kitchen tools, circuit boards, paints, adhesives, and inks. Thermosets can include the polymer of phenol or urea and combined with formaldehyde, or the polyurethane polymer, which is used for a wide variety of products including exterior automotive parts such as tires and bumpers, as well as for insulation and coating purposes. That concludes the lecture on polymer classification based on molecular force. Focus on how structure determines properties, especially the differences between elastomers, fibers, plastics, and thermosets.